Magnetic fields are invisible, yet they choreograph the entire universe. By the end of this journey, you will see how 30 hidden forces shape everything from newborn stars to the largest galaxy clusters, and even leave their fingerprints on the oldest light in the cosmos. Why does a simple magnetic field control where stars are born, and what secrets does it hold about the structure of reality itself? Deep inside cold clouds of gas and dust, gravity pulls everything inward. Without something to resist, those clouds would collapse in a cosmic hurry, turning almost all their material into monstrous stars. But the universe does not work that way. Most stars are small, light, and calm. That is because magnetic fields act as invisible brakes, slowing the entire process down. Think of a molecular cloud as a giant, slow-drifting city of gas many light years across. Threading through it are magnetic field lines like an enormous web of invisible rubber bands. As gravity tries to squeeze the cloud, the field lines get compressed and stretched. But they do not break easily. Instead, they push back. This pressure resists the collapse, allowing only certain regions to shrink. Astronomers call this magnetic braking because it literally slows the rotation and contraction of the cloud. But gravity is patient. Over time, neutral hydrogen atoms and other gas molecules drift across those field lines in a slow, quiet process called ambipolar diffusion. The magnetic field holds onto charged particles but lets neutral particles slip through. Slowly, pockets of material accumulate enough mass to overcome the magnetic support. These pockets become the seeds of future stars. The whole dance is slow and deliberate, not a runaway race. How do we know this is happening? We cannot see magnetic fields directly. But we can see their fingerprints. When starlight passes through dusty clouds, the dust grains align with the magnetic field. By measuring the polarization of that light, astronomers map the field's direction and strength. Telescopes like the Atacama Large Millimeter Array have revealed stunning images of twisted magnetic highways inside star-forming regions like the famous Orion cloud. These maps show that magnetic fields do indeed guide how gas flows and where collapse begins. This regulation has a huge consequence for the kind of stars that are born. When magnetic fields slow the collapse, less material feeds each newborn star. The result is a universe full of small, long-lived stars like our Sun, and very few of the giant, short-lived monsters. This balance is called the initial mass function, and it determines everything about a galaxy's future. A galaxy that makes mostly small stars will be dim and steady. One that makes many large stars will be bright, violent, and short-lived. Magnetic fields, by controlling the collapse, are the quiet architects of this cosmic census. So the next time you look up at a night sky full of calm, steady points of light, remember that magnetic fields help them become what they are, and those fields do not stop working after a star is born. They continue to shape what happens next. Around a newborn star, a disk of gas and dust spins slowly. This is a protoplanetary disk, the nursery where planets are born. For decades, astronomers struggled to explain one key mystery. In a simple spinning disk, material should gradually slow down and drift inward, but it should not do so nearly fast enough to build planets in the time we observe. Something must be stirring the pot. That something is magnetism. Inside the disk, gas is not perfectly smooth. It is threaded with magnetic field lines that extend from the star and the surrounding cloud. As the inner parts of the disk orbit faster than the outer parts, the field lines get stretched and twisted. This creates a powerful instability called the magnetorotational instability, or MRI for short. The MRI acts like a cosmic egg beater. It churns the gas into a turbulent, roiling mess. Turbulence is the key because it allows gas to lose energy and spiral inward, feeding the growing star while also concentrating solid particles. Without the MRI, the disk would remain calm and planet formation might never get started. the turbulence also kicks up small dust grains. These grains collide and stick together, building larger aggregates. But they need to stay in certain regions long enough to grow. Magnetic fields help here too. The turbulence driven by the aurorae creates pressure bumps and eddies, places where dust can accumulate. Think of it like a river current that sweeps leaves into a slow eddy where they pile up. In a protoplanetary disk, these dusty eddies become the seeds of planetesimals, the building blocks of planets. Over time, those planetesimals merge into full-sized worlds. The same magnetic fields also influence how planets migrate. A young planet stirs up waves in the surrounding gas. Those waves push back on the planet, sometimes gently moving it inward or outward. The planet's own magnetic field interacts with the disk's field, which can slow or steer its journey. So the magnetic environment of a young planetary system is not just a passive backdrop. It actively shapes where planets end up. How do we know all this is real? We can see it through polarized dust emission. When small dust grains align with magnetic field lines, they emit light with a distinctive orientation. Telescopes like the Atacama Large Millimeter Array have mapped this polarized light across dozens of protoplanetary disks. The images reveal rings, spirals, and gaps, all of which trace the hidden magnetic structure. These observations confirm that magnetic turbulence and disk dynamics are not theoretical. They are happening right now in nurseries across our galaxy. Our own solar system likely went through this same process billions of years ago, its magnetic threads guiding the formation of Earth and all its siblings. Today, young stars still spin with intense magnetic fields that shape their disks, creating a dynamic, ever-changing environment where planets are born, migrate, and sometimes collide. The magnetic fields that helped build the Sun never really left. They just moved on to their next great task. The Sun's magnetic field does not stay confined to its surface. It reaches out far beyond the planets, stretching an invisible web across the entire solar system. This happens because the Sun constantly releases a stream of charged particles called the solar wind, a thin, hot plasma that flows outward in all directions at speeds of hundreds of kilometers per second. As that wind travels, it carries the Sun's magnetic field along with it, dragging the field lines into interplanetary space. But the Sun does not just sit still. It rotates, completing one full turn every 25 days at its equator. So imagine the field lines as ribbons anchored to a spinning ball. As the Sun rotates, those ribbons get twisted into a grand spiral shape, coiling outward like water from a spinning sprinkler head. Scientists call this the Parker spiral, named after the astrophysicist Eugene Parker, who first predicted it in the 1950s. The Parker spiral is not just a neat pattern. It has real consequences for everything that travels through space. For example, energetic particles from distant supernova called galactic cosmic rays constantly bombard our solar system. These particles are dangerous to electronics and to living cells, so we need a shield against them. The solar wind and its embedded magnetic field create exactly that shield, an enormous bubble called the heliosphere. The heliosphere stretches from the Sun out past the orbit of Pluto, pushing back against the thin gas and dust that fills the space between stars. Within that bubble, the magnetic field is strong enough to deflect many of the incoming cosmic rays, steering them around the inner planets. Without the heliosphere, Earth would face a much harsher radiation environment, and life as we know it might never have evolved. The edge of the heliosphere is not a sharp wall but a series of boundaries. First, the solar wind slows down abruptly at a shock wave called the termination shock. Beyond that lies the heliosheath, a turbulent region where the wind piles up against interstellar material. Then comes the heliopause, the final frontier where the Sun's influence gives way to the rest of the galaxy. Human spacecraft have reached this boundary. In 2012, Voyager 1 crossed the heliopause and entered interstellar space, followed by Voyager 2 in 2018. those spacecraft are still sending back data, revealing that the heliosphere is not symmetric but shaped like a comet, with a long tail trailing behind as the sun moves through the galaxy. All of this magnetic structure originates from the sun's own magnetic activity. Sunspots, flares, and coronal mass ejections are all signs of the dynamic field that drives the solar wind. And when that wind meets a planet with its own magnetic field, the interaction becomes even more dramatic. That is exactly what happens at Earth, Jupiter, Saturn, and many other worlds. The solar wind crashes into a planet's magnetosphere, compressing it on the day side and stretching it into a long magnetotail on the night side. This collision creates electric currents, auroras, and radiation belts. So the magnetic fields of planets do not just sit quietly. They are constantly wrestling with the wind from their star, shaping the environment around them. And that battle is the next chapter in the story of how magnetic fields shape the cosmos. Earth's magnetic field is far more than a compass needle. It is a living, breathing shield, generated deep within the planet by a churning ocean of molten iron. That liquid metal, heated by radioactive decay and stirred by planetary rotation, creates a colossal electric generator called the geodynamo. Without it, the field would fade, and the story of life on this world would have taken a very different turn. The geodynamo does not just produce a static field. It constantly shifts and evolves, with the magnetic poles wandering and occasionally flipping, but the overall protection remains. This field reaches far into space, shaping a bubble known as the magnetosphere. When the solar wind, that stream of charged particles from the sun, slams into Earth's magnetosphere, it does not break through. Instead, it compresses the field on the day side and stretches it out on the night side, forming a long tail that streams away from the sun. The boundary where this battle happens is the magnetopause, a dynamic frontier that flexes and ripples with the solar wind's intensity. Inside that bubble, the field traps charged particles, creating the Van Allen radiation belts. These belts are not solid rings but vast regions of high-energy particles, mostly electrons and protons, held in place by the magnetic field, spiraling along field lines from one pole to the other. Without the magnetosphere, the solar wind would strip away Earth's atmosphere over time, just as it did on Mars, which lost its global magnetic field billions of years ago. Our world has kept its atmosphere thick and stable, allowing liquid water to persist on the surface, climates to remain moderate, and life to evolve for nearly 4 billion years. The magnetosphere does not just defend, it also lights up the sky with auroras. When the solar wind is especially strong, it can stretch and crack the magnetosphere, funneling particles down toward the poles. Those particles collide with oxygen and nitrogen in the upper atmosphere, releasing flashes of green, red, and purple. The result is a visible dance of magnetic energy, a window into the unseen struggle happening overhead every instant. So Earth's magnetic field is not a passive blanket. It is an active, breathing guardian that has shaped the conditions for life and continues to surprise us with its complexity. And this same principle applies to other worlds, some with fields far stronger or stranger, each telling a different story of how a planet interacts with its star. Magnetic reconnection turns the sky into a canvas of light. It happens when opposing magnetic field lines snap and rearrange themselves, releasing a sudden burst of energy. In Earth's magnetosphere, this process unfolds high above the poles, flinging charged particles down into the atmosphere. Those particles collide with oxygen and nitrogen, exciting them until they glow. The result is the aurora borealis in the north and the aurora australis in the south, shimmering curtains of green, red, and purple that ripple across the night. But these lights are not a steady glow. They follow a cycle called the substorm cycle, a sequence of build-up, release, and recovery. It begins when the solar wind stretches the night-side magnetosphere into a long tail. As tension grows, magnetic field lines pile up like a stretched rubber band. Then, without warning, reconnection triggers a violent snap. a surge of particles races toward the poles, producing a bright, fast-moving aurora that expands across the sky. Within minutes, the lights fade, the tail relaxes, and the magnetosphere slowly resets. This whole process repeats every few hours, driven by the sun's ever-changing wind. Space-based observatories have given us a front-row seat to this invisible drama. The Themis mission, a fleet of 5 NASA satellites launched in 2007, was designed specifically to catch substorms in the act. By flying through the magnetosphere, these probes measured the exact moment magnetic field lines broke and reconnected. Their data confirmed that reconnection is the engine behind the most dramatic auroral displays. Another mission, the Japanese-led Array satellite, studies how particles accelerate during these events, revealing that some electrons reach nearly the speed of light in seconds. Even astronauts on the International Space Station capture aurorae from orbit, watching the lights shimmering below as they circle the Earth every 90 minutes. The same principle of magnetic reconnection does not stop at aurorae. It also powers the Sun itself. On the solar surface, magnetic field lines twist and tangle as the Sun rotates. When those lines snap, they release enormous amounts of stored energy in the form of solar flares, sudden explosions of radiation that can outshine the entire Sun for minutes at a time. Flares accelerate particles into space, sometimes hurling them toward Earth where they can disrupt satellites and power grids. The connection between aurorae and flares is a direct one. Both are manifestations of magnetic reconnection, the universe's way of converting invisible tension into visible, energetic chaos. And as we move outward from the Sun, this same process repeats on other planets, each with its own magnetic field and its own sky full of light. The Sun's surface is a tangle of invisible magnetic ropes, constantly twisting and knotting as the star rotates. When those ropes snap, they release more energy than 1 billion hydrogen bombs in a single flash, a solar flare. Flares begin in active regions around sunspots where magnetic field lines are packed densely and stretched to their limit. As the Sun's differential rotation wrings these lines like a wet towel, they store immense amounts of magnetic energy. At a critical point, the field lines reconnect, breaking and rearranging into a simpler, lower-energy configuration. In that instant, the stored magnetic energy converts into heat, light, and motion. Plasma is heated to tens of millions of degrees, unleashing a burst of X-rays and ultraviolet radiation that races toward Earth at the speed of light. This is the standard flare model, called the CSHKP model after the scientists who developed it, and it describes a chain reaction that lasts from minutes to hours. But a flare is often just the beginning. Sometimes the reconnection event destabilizes a large volume of the Sun's corona, causing a massive bubble of magnetized plasma to lift off and accelerate into space. That is a coronal mass ejection, or CME. A CME can hurl billions of tons of solar material outward at speeds exceeding 1,000 kilometers per second. If one of these clouds is aimed at Earth, it takes 1 to 3 days to arrive. When it hits our planet's magnetosphere, the impact can compress the magnetic field, trigger powerful geomagnetic storms, and supercharge the auroras. But those beautiful lights come with a cost. Geomagnetic storms induced by CMEs can induce electric currents in long conductors like power lines and pipelines. In March of 1989, a CME struck Earth and caused a 9-hour blackout across the entire province of Quebec, leaving 6 million people without electricity. Satellites can suffer damage as energetic particles penetrate their electronics, and astronauts aboard the International Space Station must take shelter during severe solar particle events. High-frequency radio communications can fade, and GPS signals can become distorted, affecting everything from aviation to precision farming. The modern technological world is more vulnerable than most people realize to the mood swings of our star. Yet this same process of magnetic reconnection is not unique to the Sun. It happens in the magnetospheres of other planets, around black holes, and across the entire universe wherever magnetic fields are forced into conflict. Every time a CME launches from the Sun, we are witnessing a small-scale version of the same violent energy release that powers the most extreme objects in the cosmos. The Sun, with its predictable cycles of activity, offers us a laboratory to understand how magnetism can shape worlds, disrupt civilizations, and connect the smallest particles to the largest explosions. And as we look outward, we find that this magnetic drama repeats on Jupiter, on Saturn, and on stars far beyond our own. Magnetic reconnection is the universe's most powerful engine of change. It does not only flare on the Sun or crackle in Earth's magnetotail. It happens everywhere magnetic fields are stretched, twisted, and forced to snap into a simpler shape. That snap releases a burst of energy that can heat gas to millions of degrees, accelerate particles to near the speed of light, and drive some of the most dramatic events in the cosmos. The basic process sounds simple. When two magnetic field lines pointing in opposite directions come close together, they can break and reconnect into a new configuration shaped like an X. That rearrangement releases the energy that was stored in the original twisted fields, but the details are far from simple. The big mystery is how reconnection happens so fast in the thin, nearly collisionless plasmas that fill most of space. In a gas, particles bump into each other often, transferring energy and momentum. But in the solar corona, the Earth's magnetosphere, and the space between stars, particles travel enormous distances before colliding. They should not be able to exchange energy efficiently enough to trigger reconnection at the speeds we observe. Yet they do. The process somehow speeds up by a factor of thousands compared to simple theoretical predictions. Scientists call this puzzle collisionless reconnection. It is one of the most active frontiers in plasma physics. Observations from spacecraft like the Magnetospheric Multiscale Mission, or MMS, have flown directly through reconnection regions in Earth's magnetotail. They found that the breaking and reconnecting happens in a tiny zone only a few dozen kilometers across. Inside that zone, electric fields and wave activity accelerate electrons and ions in complex ways, essentially replacing the role of particle collisions. The particles do not bump into each other, but they do get caught in these electric fields and dance along magnetic loops, exchanging energy through collective plasma waves. That dance is the secret to the speed, but reconnection is not just a local curiosity. It is a key engine in accretion disks, the spinning rings of gas and dust that feed black holes and newborn stars. In those disks, the gas orbits at different speeds, shearing and twisting magnetic fields that thread through the disk. Turbulence driven by the magnetorotational instability amplifies those fields until they become strong enough to snap. When they snap, they release energy that heats the disk, driving some of the gas outward in powerful jets and winds while allowing the rest to spiral inward. Without reconnection, accretion disks would cool quickly and starve the central object. Reconnection keeps them hot, luminous, and active. It connects the microscopic dance of electrons in a thin plasma to the colossal glow of quasars billions of light years away. The questions that remain are profound. How exactly does collisionless reconnection work in the extreme conditions near a black hole where gravity warps space and time? Can computer simulations ever capture the full range of scales, from the tiny reconnection zone to the size of an entire disk? New missions and observatories are being designed to probe these questions, from dedicated spacecraft that will fly close to the Sun to future X-ray telescopes that will map the hottest regions around black holes. Each answer will unlock a deeper understanding of how magnetic fields shape not just individual events but the entire structure of the universe. The snap of a field line is a small act, but its consequences ripple across light years. That ripple of magnetic energy does not stop at individual stars or planets. It spreads across entire galaxies, shaping their structure and evolution on scales of hundreds of thousands of light years. How can something invisible stretch so far and remain so organized? The answer lies in a slow, self-sustaining engine called the galactic dynamo. A galaxy like our own Milky Way or the elegant spiral M51 rotates, but not like a solid wheel. Inner regions spin faster than outer ones, a phenomenon called differential rotation. This shearing motion stretches any weak magnetic field that threads through the galaxy, wrapping it into a giant spiral pattern that follows the arms. On its own, this process would simply smooth the field out over time, but another force stirs it up. That force is turbulence, supernova explosions, the winds of massive stars, and the churning of the interstellar gas create violent, chaotic motions on scales of tens to hundreds of light years. This turbulence twists the magnetic field lines in a three-dimensional dance, generating a new component that loops above and below the galactic plane. The combination of these two effects, the twisting from turbulence and the shearing from differential rotation, is known as the alpha-omega dynamo. The omega part comes from the fast rotation, the alpha part from the turbulent churning. Together, they act like a cosmic generator, taking a weak, disordered magnetic field and amplifying it into a large-scale, coherent pattern that can persist for billions of years. The dynamo does not create magnetism from nothing, but it steadily regenerates and strengthens what is already there, preventing the field from decaying away as the galaxy ages. We know this process is real because we can see its imprint. Radio telescopes detect the faint polarized glow of synchrotron radiation, light emitted by high-energy electrons spiraling along magnetic field lines. In galaxies like M51, those observations reveal stunningly ordered fields that trace the spiral arms and even extend far above the disk. The fields are not random. They follow graceful arcs often aligned with the direction of the arms, and their strength is remarkably consistent across large regions. This is exactly what the alpha-omega dynamo predicts. But these magnetic fields are not just a passive byproduct of galactic motion. They actively shape the interstellar medium, the thin gas and dust that fills the space between stars. The fields provide pressure that resists the collapse of gas clouds, regulating how stars form and how supernova remnants expand. They channel cosmic rays, energetic particles from exploded stars, forcing them to travel along field lines and sometimes trapping them for millions of years. The fields also influence the motion of gas itself, guiding flows that feed the galactic center or drive outflows into the surrounding halo. A galaxy without magnetic fields would behave very differently. Its gas collapsing faster, its star formation more violent, its cosmic rays diffusing freely instead of being held in place. The dynamo keeps these fields alive, ensuring that the magnetic influence remains steady across the lifetime of the galaxy. And as we look deeper into the cosmos, we find that this quiet engine does not just work in ordinary spirals. It operates in dwarf galaxies, in massive ellipticals, and even in the chaotic disks of high-redshift galaxies where star formation was far more intense. The same basic principles, rotation and turbulence, apply everywhere. So when you see a beautiful image of a spiral galaxy, with its arms curving outward in a perfect spiral, remember that those arms are etched not only by gravity and gas but also by the invisible magnetic skeleton that holds the whole structure together. And that skeleton has consequences that reach far beyond the galaxy itself, into the vast spaces between galaxies where magnetic fields continue their work on scales we are only beginning to understand. The magnetic skeleton of a galaxy does more than shape gas clouds and star formation. It actively controls the paths of the most energetic particles in the universe, cosmic rays. These are not rays at all, but individual particles, mostly protons and atomic nuclei, accelerated to nearly the speed of light by supernova explosions, black hole jets, or the violent flares of distant stars. Once launched, they would travel in straight lines if nothing stood in their way, but the galactic magnetic field, with its tangled spiral structure, scatters them like a maze of invisible mirrors. A cosmic ray cannot simply fly from one side of the galaxy to the other. It bounces, spirals, and zigzags along field lines, trapped for millions of years before it finally escapes. This process is called diffusion, and it is the main reason we see a smooth, steady drizzle of cosmic rays arriving at Earth rather than sharp bursts from individual sources. The magnetic field also advects cosmic rays, dragging them along with the flow of gas and plasma as it moves through the galaxy. Hot bubbles from supernova remnants push the field lines outward, carrying cosmic rays with them, spreading the particles over vast distances. The combination of diffusion and advection determines how long cosmic rays stay in the galaxy, how their energy changes over time, and what kind of signal they leave behind when they interact with gas and light. When a high-energy cosmic ray collides with a particle of interstellar gas, it can produce a flash of gamma rays, the most energetic form of light. Gamma-ray telescopes like the Fermi Space Telescope map these emissions across the sky, revealing where cosmic rays are most concentrated. The patterns they see trace the magnetic fields that guide them. In dense star-forming regions, cosmic rays pile up, producing bright gamma-ray glow. In quieter areas, they thin out. By studying the gamma-ray map, astronomers can infer the strength and structure of the magnetic field throughout the galaxy. But gamma rays are not the only messengers. When a cosmic ray collides with a proton, it can also create subatomic particles called pions, which quickly decay into neutrinos, ghost-like particles that barely interact with matter at all. Neutrino observatories like IceCube, buried in the Antarctic ice, detect these faint signals from across the universe. Each neutrino points back to the place where the cosmic ray collided, offering a direct link between the particle's origin and the magnetic field that steered it. The combination of gamma-ray and neutrino astronomy is a powerful new way to map the magnetic fields that shape the cosmos. And even closer to home, our own sun's magnetic field plays a similar role. The heliosphere, the magnetic bubble carved by the solar wind, deflects and slows the lowest energy cosmic rays before they reach Earth. This is called solar modulation, and it varies with the sun's 11-year activity cycle. During solar maximum, when the sun's magnetic field is strong and chaotic, fewer cosmic rays penetrate the inner solar system. During solar minimum, more slip through. This rhythm has been measured by neutron monitors on the ground for decades, showing that the sun's magnetic field is a living gatekeeper, constantly adjusting the cosmic ray flux that bathes our planet. The same principles that govern cosmic ray transport across the galaxy apply right here in our own backyard. The dance of particles and magnetic fields is a universal language, one that connects the smallest scales of particle physics to the largest structures in the universe. And that connection becomes even more dramatic when we zoom in on the objects that produce the most extreme magnetic fields of all. The largest planetary magnets in the solar system belong to the gas giants, and they dwarf everything Earth can produce. Jupiter's magnetic field is the strongest of any planet, stretching outward for millions of kilometers, far beyond the orbit of its largest moons. Saturn's field is weaker but still immense, and both worlds generate their magnetism through internal dynamos powered by deep layers of metallic hydrogen deep inside. Hydrogen compressed by enormous pressure into a liquid that conducts electricity like a metal. As these planets rotate rapidly, once every 10 hours or so, the churning metallic hydrogen generates a powerful magnetic dynamo, just like Earth's molten iron core but on a vastly larger scale. Jupiter's magnetosphere is so huge that if it were visible from Earth, it would appear larger than the full moon in the sky. It traps and accelerates particles, creating intense radiation belts that can damage spacecraft and pose serious challenges for missions like Juno, which has been orbiting the giant planet since 2016. One of the most fascinating phenomena inside Jupiter's magnetosphere comes from its moon Io. Io is the most volcanically active body in the solar system, constantly erupting with sulfur and sulfur dioxide. Those gases become ionized by Jupiter's radiation and are swept up by the magnetic field, forming a donut-shaped ring of plasma called the Io plasma torus. This torus glows in ultraviolet light and feeds particles into Jupiter's auroras, creating a shimmering light show that is far more powerful than anything on Earth. The torus also interacts with Jupiter's magnetic field, generating powerful electrical currents that flow along field lines connecting the planet to the Moon. This is called the Io flux tube, a direct magnetic link between a world and its Moon. As Io orbits every 42 hours, it moves through Jupiter's field, acting like a generator and producing about 1 trillion watts of power. That energy heats the torus and drives complex radio emissions that we can detect from Earth. Saturn's magnetosphere is quieter but equally fascinating. Its internal dynamo produces a surprisingly symmetrical field, one of the most perfectly aligned with the planet's rotation axis in the solar system. The reason for this alignment remains a mystery, but it affects how the magnetosphere interacts with Saturn's rings and moons. Saturn's moon Enceladus sprays water vapor and ice particles into space from its south pole, and those particles become ionized and feed a faint plasma torus around the planet. The interaction between Enceladus plumes and Saturn's magnetic field generates auroral spots at the footprint of the Moon's magnetic connection, similar to what happens at Jupiter with Io. The gas giants do not just have big magnetospheres, they have entire families of moons that swim within those invisible seas, each one creating its own magnetic disturbance, each one a new place where the fields of a planet and its satellite meet. And that meeting is not a quiet one. It is a constant dynamic exchange of energy and matter that shapes both the moons and the magnetospheres themselves. The next step in understanding this relationship is to look at the moons that have their own magnetic fields, worlds like Ganymede, the only moon in the solar system known to generate its own magnetosphere. The dance between a planet's field and a moon's field creates a hidden landscape of magnetic frontiers, and that is where the story becomes even more surprising. Europa's hidden ocean reveals itself through magnetic fingerprints. As Jupiter rotates every 10 hours, its powerful magnetic field sweeps past the Moon, constantly changing in strength and direction. Europa, with its global saltwater ocean beneath an icy crust, acts like a conductor. That moving magnetic field induces an electric current inside the ocean, which in turn generates a secondary magnetic field, one that opposes the change and can be detected from orbit. When NASA Galileo spacecraft flew by Europa in the late 1990s, its magnetometer registered a clear signature, a telltale wobble that matched exactly what an induced field would produce. This was the first solid evidence that a liquid, electrically conductive layer existed beneath the ice, and it pointed directly to a subsurface ocean. Since then, the same technique has been applied to Jupiter's moon Callisto and Saturn's moon Enceladus, each showing similar magnetic hints of hidden water. Ganymede stands apart as the only moon in the solar system with its own intrinsic magnetic field, generated by a molten iron core deep inside. That field creates a tiny magnetosphere within Jupiter's, a bubble that deflects the incoming plasma and carves out a distinct cavity. The boundary where the two fields meet is a site of magnetic reconnection, releasing energy and accelerating particles. But even Ganymede's interior seems to hold a liquid layer, detected through subtle variations in its own magnetic field as it moves through Jupiter's magnetosphere. The implications for habitability are profound. Liquid water, a key ingredient for life as we know it, appears to be common among the icy moons of the outer solar system. But water alone is not enough. The interaction between these subsurface oceans and the planetary magnetospheres provides energy, a source of chemical disequilibrium that could power the reactions needed for life. At Enceladus, the Cassini spacecraft flew directly through plumes of water vapor and ice particles erupting from the South Pole. Those plumes are ionized by Saturn's magnetic field and swept into a torus around the planet, creating faint auroral spots at the Moon's magnetic footprint. The material in the plumes contains organic compounds and simple salts, hinting at hydrothermal activity on the seafloor beneath the ice. Magnetic interactions are not just passive indicators. They actively shape these moons, heating their interiors through tidal forces and inducing electrical currents that dissipate energy. Every spacecraft that has measured magnetic field perturbations around these worlds has added another piece to the puzzle. And as we prepare missions like Europa Clipper and the Jupiter Icy Moons Explorer, the magnetometers on board will map these fields in unprecedented detail, revealing the depth, salinity, and even the circulation of the hidden oceans. But not all moons are so active. Beyond the giant planets, there are airless bodies, the Moon, Mercury, and countless asteroids. These worlds have no global magnetic fields today, but their crusts retain remnant magnetism locked in ancient rocks. The Moon's surface, for example, holds patches of strong magnetization, relicts of a time when the lunar core was alive with a dynamo, or perhaps magnetized by large impacts that generated transient fields. By mapping these magnetic scars, scientists piece together the early history of the solar system, a time when small bodies held their own magnetic secrets. In the end, every moon and every asteroid tells a different magnetic story, and those stories are just beginning to be read. The Moon today has no global magnetic field, but its crust holds fossilized memories of a lost dynamo. When Apollo astronauts brought back lunar rocks, scientists found something strange. Some of those rocks were magnetized, as if they had been cooled in a strong magnetic field billions of years ago. Yet the Moon has no such field now. This remnant magnetization is a ghost of a time when the lunar core was molten and churning, generating a dynamo similar to Earth's but much weaker. That dynamo likely lasted for only a few 100 million years before the Moon's small core cooled and solidified. Once the magnetic field faded, the Moon lost its protective shield. The solar wind, a constant stream of charged particles from the Sun, could then strike the lunar surface directly, stripping away lighter elements and eroding the fragile atmosphere that may have once existed. Over eons, the Moon became the dry, airless world we see today. Mars tells a similar but more dramatic story. Today, the red planet lacks a global magnetic field. But spacecraft orbiting Mars have detected patches of strong magnetization in its ancient southern highlands, bands of crust that are magnetized with alternating polarity. These stripes look like the magnetic record left on Earth's seafloor as tectonic plates spread, but on Mars they are frozen into terrain that is billions of years old. The pattern tells researchers that Mars once had an active dynamo, a molten iron core that generated a global field, probably for the first 500 million years of its history. Then something went wrong. The dynamo shut down, perhaps because the core cooled too quickly or because mantle convection changed. Without a magnetic shield, the Martian atmosphere was exposed to the full force of the solar wind. Energetic particles from the Sun gradually stripped away lighter gases like hydrogen and oxygen, which escaped into space. Over time, the thick, warm atmosphere that allowed liquid water to flow on the surface thinned to less than 1% of Earth's pressure. The water either froze underground or escaped into space, leaving behind a cold, arid desert. The loss of a planet's magnetic field is not just a curiosity. It is a fundamental factor in whether a world can retain the conditions for life. This is why scientists studying exoplanets pay close attention to magnetic fields. A planet without a strong magnetosphere may lose its atmosphere and water, becoming a barren rock. But if that same planet sits too close to a flaring star, a strong field might instead trap dangerous particles and intensify radiation. The balance is delicate. Now consider what happens when magnetic fields are not lost but amplified beyond imagination. Some objects in the cosmos pack more magnetic energy into a region the size of a city than the entire Sun produces. These are neutron stars, the collapsed cores of massive stars that ended their lives in supernova explosions. Their magnetic fields reach trillions of times Earth's strength, so intense that they warp the very fabric of space around them. The transition from a world without a field to an object where the field dominates everything could not be starker. And in that extreme, we find some of the most violent and mysterious events in the universe. Neutron stars collapse into spheres just kilometers wide, but their magnetic fields reach quadrillions of times Earth's strength. These are magnetars, the most intensely magnetic objects known. Their fields are so powerful that they warp the atomic structure of matter itself. If a magnetar drifted within a few 100,000 kilometers of Earth, its magnetic field would disrupt our planet's own field, erase data from every credit card and hard drive, and induce electric currents strong enough to damage power grids. Fortunately, none are that close, but across the galaxy, about 30 confirmed magnetars lurk, and their behavior is unlike anything else. The extreme field does not just sit quietly. It twists and stresses the neutron star's solid crust, which is a rigid shell of iron and other nuclei held together by unimaginable pressure. When the strain becomes too great, the crust cracks in a starquake, releasing a sudden burst of energy. That energy erupts as a giant flare, a blast of gamma rays and X-rays that can outshine the entire galaxy for a fraction of a second. Such flares are called soft gamma repeaters because they repeat at irregular intervals, often years apart. The first one, detected in 1979, was so powerful that it saturated detectors on multiple spacecraft and was observed across the solar system. Scientists initially thought it might be a nuclear test on Earth, but its origin traced back to a known supernova remnant in the Large Magellanic Cloud, a small galaxy orbiting our own. These flares are not the only signature. The magnetic field of a magnetar also affects how quickly it spins down. A normal neutron star, called a pulsar, rotates steadily and slows down gradually as it loses energy through magnetic braking. For a magnetar, the spin down is far more dramatic. The intense field extracts rotational energy much faster, so magnetars spin down to long periods of several seconds within just a few thousand years, much younger than typical pulsars. This rapid spin down makes them rare and short-lived. They are visible for only about 10,000 years before their magnetic activity fades and they become quiet, dead stars. In recent years, a surprising connection has emerged between magnetars and fast radio bursts, mysterious millisecond-long flashes of radio energy that come from across the universe. In 2020, a magnetar in our own galaxy, called SGR 1935+2154, emitted a radio burst that was detected by the CHIME telescope. This burst was 1,000 times weaker than the extragalactic fast radio bursts, but its structure was identical. For the first time, astronomers had direct evidence that at least some fast radio bursts come from magnetars. The leading theory is that a starquake or a sudden reconnection event in the magnetosphere releases a blast of plasma that generates a coherent radio pulse. The energy and timescale match, so these tiny magnetic monsters are likely responsible for one of the most enigmatic signals in modern astronomy. Yet the story does not end with explosions. A magnetar that does not flare can still be a steady beacon of radio light, a pulsar. Pulsars are neutron stars that beam radio waves from their magnetic poles as they rotate like a cosmic lighthouse. Their radio emission comes from the acceleration of charged particles along open magnetic field lines above the poles, producing a narrow beam that sweeps past Earth with every rotation. The immense magnetic field of a pulsar generates electric fields strong enough to tear particles from the surface and accelerate them to near light speed. Those particles produce a cascade of radio waves through a process called coherent curvature radiation. The same magnetic field that drives the pulsar's engine also determines its lighthouse beam's shape, intensity, and stability. Magnetars, with their extreme fields, can sometimes produce pulsar-like emission as well, but it is often erratic and embedded in X-rays. The boundary between magnetar and ordinary pulsar is not sharp, and some neutron stars seem to switch between behaviors as their fields decay. These objects are laboratories of physics at its most extreme, where gravity, magnetism, and quantum mechanics meet. As we move further into the cosmos, the same magnetic forces that twist a neutron star into a flaring magnet or a steady pulsar also shape objects on vastly larger scales, where entire galaxies become cosmic engines driven by magnetic fields. Thousands of quiet, spinning neutron stars pulse with radio light. These are pulsars, and their magnetic fields do not just store energy, they shape a beacon that sweeps across the cosmos. The key is the axis. When a massive star collapses into a neutron star, its magnetic field gets compressed and intensified, and the star's rotation speeds up dramatically. The magnetic field axis usually points at an angle to the rotation axis, like a tilted bar magnet. As the star spins, the magnetic poles rotate in a circle, and any charged particles trapped near those poles get accelerated into narrow beams of radiation. The beams shoot out from both poles, and if one of them happens to sweep past Earth, we detect a regular pulse of radio waves with every rotation. This is the lighthouse effect, named after the way a lighthouse beam appears to flash as it rotates. The radio emission does not come from the entire star. It originates from specific regions above the magnetic poles where the field lines open outward rather than closing back onto the star. The most widely accepted model, the polar cap model, says that these open field lines become a site where strong electric fields tear particles from the surface and accelerate them along curved paths, producing radio waves through a process called coherent curvature radiation. The particles radiate in sync, creating a powerful and directed burst. An alternative model, the slot gap, proposes that the emission comes from a narrow gap between open and closed field lines, a region shaped like a thin hollow cone around the magnetic pole. This slot gap can produce a broader, more complex beam, sometimes causing pulsars to show two separate peaks in their radio profile as the cone sweeps past. Both models help explain the rich variety of pulse shapes astronomers see, from simple single peaks to multi-peaked structures that reveal the geometry of the magnetic field. What makes pulsars truly remarkable is the astonishing regularity of their pulses. The rotation of a neutron star is incredibly stable, often rivaling the precision of atomic clocks on Earth. The pulses arrive with such exact timing that astronomers can detect tiny deviations caused by the presence of orbiting planets, the gravitational influence of a companion star, or even the slow loss of rotational energy as the magnetic field extracts angular momentum. This timing stability has been used to confirm predictions of general relativity, such as the orbital decay of binary pulsars due to gravitational waves, a discovery that earned a Nobel Prize. Pulsar timing arrays are now being used to detect nanohertz frequency gravitational waves rippling through the galaxy, turning these spinning magnetic lighthouses into a galaxy-sized gravitational wave detector. The magnetic field that powers the pulsar is also what slowly drains its energy. As the magnetic dipole rotates, it radiates electromagnetic waves, sapping the star's rotational energy and causing it to slow down over millions of years. Eventually, the rotation becomes too slow to sustain the radio emission, and the pulsar dies, becoming a quiet, cold neutron star. This same magnetic extraction of rotational energy, however, has a far more dramatic counterpart in systems where a spinning black hole is surrounded by a swirling disk of gas. The black hole's own magnetic field, anchored in the accretion disk, can tap into the rotation of the hole itself, launching powerful jets that spear through the surrounding galaxy. The principles that govern a pulsar's lighthouse beam, the twisting of field lines, the acceleration of particles, the beaming of energy, scale up to the most powerful engines in the universe. From a spinning stellar corpse to a supermassive black hole, magnetism is the invisible hand that compels matter to move, radiate, and escape. Around a spinning black hole, magnetic fields become the engines of the most powerful jets in the universe. But those jets do not simply appear from nowhere. They are born in the churning disk of gas and dust that spirals into the black hole, a structure called an accretion disk. As gas in the disk orbits faster on the inside than on the outside, it drags and twists any magnetic field lines that thread through it. This shearing motion drives a powerful instability, the same magnetorotational instability that stirs protoplanetary disks, but on an immensely larger scale. In an accretion disk, the aurorae creates turbulence that allows gas to lose its angular momentum and fall inward, feeding the black hole at a steady rate. Without that magnetic stirring, the disk would remain smooth and gas would pile up, starving the black hole and preventing the brilliant light we observe. But the aurorae does more than just feed the black hole. It amplifies the magnetic field, winding it into a tight, ordered structure that grows stronger with each orbit. Some of those field lines become anchored in the disk and stretch far outward. Others thread the event horizon itself, the point of no return, and that is where the Blandford-Zeeman process takes over. Imagine a spinning black hole wrapped in magnetic field lines that are rooted in the surrounding disk. As the black hole rotates, it drags these field lines along with it, like a spinning magnet inside a coil. This spinning magnetic field generates a powerful electric current, turning the black hole into a cosmic battery. The voltage is enormous, enough to accelerate particles near the speed of light. Those particles stream outward along the field lines, forming twin jets that blast away from the black hole at 99.99% of the speed of light. The jets carry away some of the black hole's rotational energy, gradually slowing its spin over millions of years, but in the process, they light up the surrounding galaxy with radio waves, X-rays, and gamma rays. The most famous example is the jet from the supermassive black hole at the center of galaxy M87. In 2019, the Event Horizon Telescope captured the first direct image of that black hole's shadow, surrounded by a bright ring of hot gas. But even before that image, astronomers had observed M87's jet stretching for thousands of light years, a visible column of plasma powered by magnetic fields. The observations matched theoretical models of the Blandford-Zeeman process almost perfectly, confirming that magnetic extraction of rotational energy is real and happening right now in galaxies across the universe. These active galactic nuclei, or AN, are among the brightest objects in the cosmos, outshining all the stars in their host galaxies. Their jets can extend far beyond the galaxy, injecting energy and magnetic fields into the intergalactic medium, shaping the large-scale structure of the universe. From a single spinning black hole to the filaments that connect galaxy clusters, magnetic fields continue their relentless work, binding, accelerating, and transforming matter on every scale imaginable. Those jets that blast away from a spinning black hole do not stay as narrow beams forever. Without something to shape them, they would spread out, lose their energy, and dissolve into the surrounding gas. But magnetic fields act like invisible nozzles, collimating the jets into tight, focused columns that can travel for hundreds of thousands of light years without dispersing. The process begins in the immediate vicinity of the black hole, where the magnetic field lines are anchored in the accretion disk and also thread the event horizon itself. As the black hole spins, it twists these field lines into a helical structure, a spring-like configuration that wraps around the jet. This helical magnetic field exerts a pinching force, squeezing the plasma inward and preventing it from expanding sideways. The stronger the spin of the black hole, the tighter the twist, and the more collimated the jet becomes. Astronomers have measured this effect directly using polarization observations. When light from the jet passes through aligned magnetic fields, its polarization angle rotates, a phenomenon called Faraday rotation. By mapping how much the polarization rotates across the jet, researchers can reconstruct the three-dimensional structure of the magnetic field. In the famous jet of M87, these measurements reveal a strong, ordered helical field that remains stable for thousands of light years. The jet not only stays narrow but also accelerates. As the magnetic field unwinds, it transfers energy to the plasma, pushing it to speeds close to the speed of light. The acceleration is gradual, with the jet gaining speed over distances of tens of thousands of light years. This magnetic acceleration mechanism explains why the fastest parts of the jet are often seen far from the black hole, not at its base. The jets do more than just look dramatic. They inject enormous amounts of energy and magnetic flux into the surrounding galaxy, heating the interstellar gas and blowing massive bubbles of hot plasma into the intergalactic medium. This feedback process can suppress star formation in the host galaxy, preventing it from growing too large or too quickly. In massive elliptical galaxies, the central supermassive black hole and its jets act like a cosmic thermostat, regulating the temperature of the gas and dictating how many new stars can form. Without this magnetic feedback, galaxies would consume their gas too fast and evolve into different shapes. The same magnetic fields that collimate the jets also leave their imprint on the larger galactic environment. As the jets expand, they drag the interstellar magnetic field along with them, stretching and ordering it on scales of tens of thousands of light years. This creates vast magnetic structures that can be detected through radio observations of diffuse synchrotron emission. The result is a seamless connection between the black hole's magnetosphere and the magnetic field of the entire galaxy, a hidden scaffolding that links the smallest engine to the largest structures. And that scaffolding does not stop at the galaxy's edge. It reaches out into the space between galaxies where the relics of ancient jets still glow faintly, whispering the magnetic history of the cosmos. That history is written into the very structure of our own galaxy. The Milky Way is not just a swirling disk of stars, gas, and dust. It is also laced with a vast, ordered magnetic field that spirals outward from the center to the edge, an invisible skeleton that holds the galaxy together and shapes everything inside it. Astronomers have mapped this field using two powerful tools, Faraday rotation and synchrotron emission. Faraday rotation happens when polarized radio light from distant sources like pulsars or quasars passes through the magnetized plasma of the galaxy. The magnetic field twists the light's polarization angle, and by measuring how much it twists, scientists can calculate the strength and direction of the field along the entire line of sight. The result is a three-dimensional map of the Milky Way's magnetic structure, revealing that the field follows a spiral pattern roughly aligning with the galaxy's arms. This pattern is not perfect. There are twists, bubbles, and regions where the field reverses direction, hints of past disturbances from supernova explosions or the passage of satellite galaxies. Synchrotron emission gives a complementary view. High-energy electrons, accelerated by supernova shocks and other violent events, spiral along magnetic field lines and emit radio waves. Maps of this diffuse glow show a diffuse, patchy signal that traces the same spiral structure, with brighter emission in the inner galaxy and along the arms where star formation is most active. Together, these two techniques reveal that the Milky Way's magnetic field is not a static feature. It is a living, dynamic entity shaped by the same forces that drive the stars. And it plays a critical role in controlling the lives of those stars. The magnetic field confines cosmic rays, those high-energy particles that zip through the galaxy at nearly the speed of light. Without the field, cosmic rays would escape in only a few thousand years, barely interacting with the interstellar gas. but the magnetic field acts like a maze, scattering them and trapping them for millions of years. This confinement allows cosmic rays to build up, and when they eventually collide with gas atoms, they produce gamma rays and secondary particles. The result is a glow that lights up the entire galaxy in gamma-ray light, a glow that the Fermi telescope sees every day. This trapped population of cosmic rays also influences the chemistry of the interstellar medium. They ionize neutral gas, creating free electrons that affect how molecular clouds collapse. They heat the gas, providing pressure that can resist gravity. In this way, the magnetic field indirectly regulates how fast stars form, slowing the process and spreading it out over time. But the field does not just confine cosmic rays. It also guides the flow of the interstellar medium itself. The gas between stars is not a static fog. It is a turbulent, magnetized fluid, constantly churning under the influence of supernova shock waves, stellar winds, and the rotation of the galaxy. The magnetic field threads through this fluid, providing a restoring force that dampens turbulence and prevents gas clouds from collapsing too quickly. It also channels the gas into the spiral arms, feeding the regions where new stars will be born. Without this magnetic guidance, the gas would spread more evenly, and the galaxy's elegant spiral pattern might not survive. The field even reaches above and below the galactic disk, forming a magnetized halo that extends thousands of light years. This halo interacts with the cosmic web, the network of filaments that connect galaxies across the universe. Some of the gas and magnetic flux from our galaxy may even leak out into intergalactic space, contributing to the faint magnetic fields that permeate the cosmos. So the Milky Way's magnetic field is not just a passive backdrop, it is an active agent shaping the galaxy's evolution from the inside out. And as we zoom in on the spaces between the stars, we find that this same magnetic influence extends to the smallest scales, governing the behavior of the interstellar medium in ways that continue to surprise us. The spaces between stars are not truly empty. They are filled with a thin, diffuse mixture of gas and dust called the interstellar medium, and threaded through it runs a weak but pervasive magnetic field. This field is far fainter than the one that holds a fridge magnet to a door, only a few microgauss, about 100,000 times weaker than Earth's surface field. Yet over distances of light years, that feeble magnetic grip exerts a powerful influence, shaping how gas moves, how clouds form, and how new stars eventually ignite. The key to this influence is the way the magnetic field couples to the ionized component of the interstellar medium. Not all atoms in the diffuse gas are neutral. Some are stripped of electrons by ultraviolet light from hot stars or by cosmic ray collisions, creating a plasma of free electrons and positive ions. These charged particles are forced to spiral along magnetic field lines, locked in place by the Lorentz force. They cannot cross the field lines easily. Neutral atoms, on the other hand, can drift across the field, but they constantly collide with the ions and electrons, transferring momentum. This coupling means that the entire gas, both charged and neutral, behaves as a single magnetized fluid. The magnetic field provides a restoring force, a kind of tension that resists compression and bending. When a shock wave from a supernova or a stellar wind pushes against the gas, the field pushes back, damping the motion and smoothing out turbulence. Without this magnetic support, the interstellar medium would be far more chaotic, with gas clouds collapsing too quickly and forming stars in violent bursts rather than the gradual, regulated way we observe. One of the most striking consequences of this magnetic coupling is how it influences the formation of dense clouds, the nurseries where new stars are born. The diffuse interstellar medium is not uniform. It contains regions where gas has been swept up by old supernova remnants or spiral density waves, creating sheets and filaments. As these structures compress, the magnetic field lines get squeezed together, increasing the field strength. The magnetic pressure rises in response, resisting further collapse. This creates a delicate balance. For a cloud to become dense enough to form stars, the gas must overcome the magnetic support. It does so through processes like ambipolar diffusion, where neutral gas slips slowly across the field lines, or through turbulent compression that temporarily overwhelms the field. The magnetic field thus acts as a gatekeeper, determining which regions can collapse and at what speed. And because star formation is the engine that drives galactic evolution, this magnetic regulation affects the entire life cycle of a galaxy. But how do we actually detect these invisible fields in the diffuse interstellar medium? One powerful method relies on the alignment of dust grains. Dust grains in space are not perfect spheres. They are irregular, often elongated like tiny footballs. When a magnetic field is present, these grains tend to spin and align themselves with their long axis perpendicular to the field lines, like compass needles but for magnetism. The exact mechanism is complex and involves the interaction of the grain's rotation, its electric charge, and the surrounding gas, but the result is that the dust grains become partially aligned. When starlight passes through a region of aligned dust, the light becomes polarized, meaning its electric field oscillates in a preferred direction. By measuring the degree and orientation of this polarization, astronomers can map the direction of the magnetic field in the intervening cloud. This technique, called polarimetry, has revealed the magnetic skeletons of countless interstellar clouds, showing twisted filaments and ordered patterns that trace the hidden forces at work. Another direct measurement technique is the Zeeman effect, named after the Dutch physicist Pieter Zeeman. When atoms or molecules are placed in a magnetic field, their energy levels split slightly, causing spectral lines to split into multiple components. The amount of splitting is proportional to the strength of the magnetic field. By observing certain spectral lines, like the 21-centimeter line of neutral hydrogen, with very high precision, astronomers can detect this splitting and directly measure the magnetic field strength along the line of sight. The Zeeman effect is challenging because the splitting is tiny, often much smaller than the width of the spectral line itself. But with sensitive radio telescopes, it has been used to measure magnetic fields in hundreds of interstellar clouds, confirming that these fields are indeed present and strong enough to influence the gas dynamics. The combination of dust polarization and Zeeman measurements gives us a complementary view, one mapping direction, the other mapping strength. Together, they reveal a universe where even the most tenuous gas is magnetically structured, a web of invisible threads that binds the cosmos together, guiding the slow dance of matter between the stars. One of the most direct ways to measure a magnetic field in space comes from the splitting of spectral lines. This is the Zeeman effect, named after the Dutch physicist who first described it in the late 19th century. When atoms or molecules sit inside a magnetic field, their energy levels shift slightly, splitting into multiple components. That splitting causes a single spectral line to break into 2 or 3 separate lines, depending on the geometry of the field. The distance between those split lines is tiny, often much smaller than the natural width of the original line itself, but it is proportional to the strength of the magnetic field. So by measuring that separation with extreme precision, astronomers can directly calculate how strong the field is along their line of sight. This technique has been applied to molecular clouds, the dense, cold regions where stars are born. In places like the Orion molecular cloud, radio telescopes have detected the Zeeman splitting of the 21-centimeter line of neutral hydrogen, as well as lines from molecules like hydroxyl and cyanogen. The results show that typical magnetic field strengths in these clouds range from a few microgauss to several dozen microgauss, weak by everyday standards but powerful enough to resist the pull of gravity over entire light years. The Zeeman effect has also been used in H2 regions, the glowing clouds of ionized gas surrounding hot young stars. There, the field can reach tens to hundreds of microgauss, shaped by the violent winds and radiation from the embedded stars. But the method has limitations. The splitting is so small that it is often hidden within the natural spread of the line. Detecting it requires long observations with sensitive radio telescopes and careful removal of other effects. It only measures the component of the field along the line of sight, not its full three-dimensional direction, and it works best in regions where the gas is dense enough to produce a strong spectral line. Despite these challenges, the Zeeman effect remains one of the few ways to get an absolute, model-independent measurement of magnetic field strength in the interstellar medium. Each successful detection adds a data point to the map of the hidden magnetic universe. To complement these strength measurements, astronomers turn to another technique that reveals the field's direction and structure along the entire path the light travels. That method is Faraday rotation. When polarized radio light passes through a magnetized plasma, its polarization angle rotates. The amount of rotation depends on the strength of the magnetic field and the density of free electrons along the line of sight. By measuring the rotation of a known polarized source, like a pulsar or a distant quasar, scientists can calculate the integrated magnetic field over that path. This gives a different kind of information, not the field strength at one point, but the average field weighted by electron density across the whole journey. Together, the Zeeman effect and Faraday rotation form a powerful pair. One pins down the strength at specific locations, the other traces the field's influence across vast distances. Between them, they have revealed that magnetic fields are not just curiosities but integral parts of how the interstellar medium behaves, channeling gas, guiding cosmic rays, and shaping the very clouds where stars will one day ignite. Faraday rotation turns polarized light into a cosmic measuring tape, one that stretches across billions of light years. When a distant source, like a pulsar or a quasar, emits radio waves that are polarized in a particular orientation, those waves travel through the thin, magnetized plasma that fills the space between galaxies. That plasma contains free electrons, and those electrons interact with the radio waves, twisting their polarization angle as they pass. The amount of twist depends on two things: the strength of the magnetic field along the path and the density of free electrons. This twist is predictable, and by measuring it, astronomers calculate a number called the rotation measure. The rotation measure is a single number that encodes the average magnetic field strength weighted by electron density all the way from the source to the telescope. A single rotation measure gives a single data point, but when you combine hundreds of thousands of them, you can build a three-dimensional map of the magnetic field across an entire galaxy or even a cluster of galaxies. That is exactly what surveys like RMGrid are doing. RMGrid is a global effort that brings together data from multiple radio telescopes, including the Very Large Array in New Mexico and the Australian Square Kilometre Array Pathfinder. By measuring the rotation measure of millions of background sources, RMGrid is mapping the magnetic structure of our own Milky Way and beyond, revealing how the field twists, reverses, and spirals through the interstellar medium. The same technique works on galaxy clusters, where the hot, ionized gas between galaxies produces a strong Faraday rotation signature. For example, observations of the Perseus cluster have shown that its central magnetic field is tangled and amplified by turbulence from the active black hole at its heart. These rotation measure maps have become one of the most powerful tools in extragalactic astronomy, allowing researchers to see the invisible magnetic scaffolding that holds clusters together and channels the flow of hot gas. But Faraday rotation only tells part of the story. It measures the effect of the field on light that passes through it, not the light that the field itself produces. To see the field directly, astronomers turn to another technique, one where the magnetic field generates its own glow. That glow is synchrotron radiation, and it is about to give us a completely different view of the cosmos. That glow is synchrotron radiation, and it is about to give us a completely different view of the cosmos. When a high-energy electron races through a magnetic field, it does not move in a straight line. It spirals, forced into a tight corkscrew path by the invisible grip of the field. As it accelerates around each turn, it releases a burst of light. This light spans a vast range of wavelengths, from long radio waves all the way up to high-energy gamma rays. The faster the electron and the stronger the magnetic field, the more energetic the emitted radiation becomes. This process, called synchrotron radiation, is one of the most important tools astronomers have for seeing magnetic fields across the universe. The radiation itself carries a wealth of information. Its total brightness tells us how many high-energy electrons are present and how strong the magnetic field is that bends their path. Its spectrum, the way the brightness changes with wavelength, reveals the distribution of particle energies, and its polarization, the orientation of the electric field in the light wave, directly traces the direction of the magnetic field lines. When we see a region glowing strongly in radio waves with a high degree of polarization, we know we are looking at a place where magnetic fields dominate the behavior of fast-moving particles. Supernova remnants offer some of the clearest examples. When a massive star explodes, it sends a shock wave hurtling through the surrounding gas. That shock accelerates electrons to nearly the speed of light, and the magnetic field left behind by the explosion, often amplified by the shock itself, makes them spiral and shine. The Crab Nebula, the remains of a star that exploded in the year 1054, glows brilliantly in radio, optical, and X-ray light, all from synchrotron radiation. Its magnetic field is so strong and so ordered that we can see detailed filaments of polarized light winding through the nebula. By studying those filaments, astronomers have measured the field strength right inside the remnant and watched how it evolves as the nebula expands. The same process operates on vastly larger scales in radio galaxies. When a supermassive black hole launches jets of plasma at nearly the speed of light, those jets are filled with relativistic electrons and magnetic fields. As the jets plow into the intergalactic medium, they create giant lobes of radio emission, often spanning hundreds of thousands of light-years. The synchrotron glow from these lobes is how we first discovered many active galaxies in the 20th century. Each lobe is a storehouse of magnetic energy, and its structure tells us how the jets have swum through the surrounding gas, how the field has been stretched and tangled, and how much power the black hole has poured out over millions of years. But synchrotron radiation does not only come from dramatic explosions and active nuclei. It also comes from the faintest, most diffuse structures in the universe, the cosmic web filaments that connect galaxies. Between the vast voids of space, gas is thinly spread in long, thread-like networks. That gas is hot and partially ionized, and it contains a very weak magnetic field, only a billionth of Earth's magnetic strength. Yet even that faint field is enough to make any high-energy electrons present emit a dim, ghostly radio glow. Detecting that glow is extremely difficult because it is so faint, but with sensitive radio telescopes, astronomers have begun to see it. Observations of galaxy clusters like the Coma cluster reveal diffuse radio emission that cannot be tied to any individual galaxy, tracing the magnetic fields that fill the entire cluster. The signal is so faint that it takes hundreds of hours of telescope time to pick it up, but it is there, a whisper from the hidden magnetic fabric of the cosmic web. This radio glow from the web tells us something profound. The magnetic fields of the universe are not confined to stars, galaxies, or clusters. They permeate the largest structures we know, carried by the same gas that collapses into galaxies and clusters. The synchrotron radiation we see from these filaments is a direct measurement of those fields, a beacon from the invisible skeleton that binds the cosmos together. And the photons that reach our telescopes have traveled across billions of light-years, carrying the imprint of fields so weak that they barely register on any instrument, yet so pervasive that they shape the very structure of reality. Each radio wave that lands on a dish on Earth is a message from the magnetic universe, written in the language of light itself. That faint radio glow reaches us from the vast spaces between galaxies. It comes from the cosmic web, the network of thin filaments that stretch across the universe, connecting galaxies and galaxy clusters like threads in a gigantic spider web. Between the great voids of nearly empty space, gas flows along these filaments, and that gas is not completely alone. It carries with it magnetic fields so weak that they register at only a billionth of the strength of Earth's field, yet they are present, threading through the largest structures we know. How do we detect something so faint? Two methods, both already familiar, come into play across these intergalactic distances. When a distant quasar or a fast radio burst sends polarized light toward Earth, that light passes through the magnetized plasma of a cosmic filament. The free electrons in the filament twist the light's polarization, producing a Faraday rotation signal that encodes the average magnetic field along that line of sight. By measuring these rotations for thousands of background sources, astronomers have built maps that reveal magnetic fields stretching across tens of millions of light years. The synchrotron emission from those same filaments, though incredibly dim, has also been glimpsed by the most sensitive radio telescopes. That emission comes from high-energy electrons that spiral along the field lines, and its detection confirms that the fields are real and widespread. The origin of these intergalactic fields remains an open question, and it points to two broad possibilities. One is that they are primordial, leftover from the very early universe. In the first moments after the Big Bang, tiny quantum fluctuations could have seeded weak magnetic fields that were later amplified by the turbulent motions of cosmic gas as galaxies and clusters formed. The other possibility is that these fields were seeded later by astrophysical processes. As galaxies formed and evolved, they expelled magnetized gas through supernova winds and black hole jets. That enriched material flowed into the cosmic web, carrying its magnetic fields along with it. The truth may be a combination of both, with a primordial background enhanced by later injections from galaxies. Regardless of their origin, these magnetic fields play a crucial role in the structure formation of the universe. They provide pressure that resists the collapse of gas into galaxies, slowing the flow of material along filaments and influencing how much gas can actually feed a growing galaxy. They also channel cosmic rays, the high-energy particles that travel between galaxies, guiding their paths and affecting the heating and ionization of the intergalactic medium. Without magnetic fields, gas would stream more freely, and the process of galaxy formation might be faster and more chaotic. The fields act as a gentle regulator, an invisible hand that shapes the large-scale cosmic landscape. As we zoom in from the vast web of filaments, we encounter the densest nodes of that web, the places where many filaments converge. These are galaxy clusters, the largest gravitationally bound structures in the universe. And inside clusters, the magnetic fields are no longer faint. They become tangled, amplified by the turbulent motions of hot gas and the violent activity of thousands of galaxies. The same techniques that revealed the weak fields of filaments, Faraday rotation, and synchrotron emission now show us fields that are hundreds of times stronger, stretching across millions of light years. That transition from the faint whisper of the cosmic web to the louder roar of a cluster is where our story of magnetic influence continues. In the densest nodes of the cosmic web, magnetic fields surge to life with far greater intensity. Galaxy clusters are the largest gravitationally bound structures in the universe, containing thousands of galaxies swimming in a sea of hot, X-ray emitting gas called the intracluster medium. This gas reaches temperatures of tens of millions of degrees, and it is threaded with magnetic fields that are hundreds to thousands of times stronger than those in the faint cosmic filaments. These fields typically measure a few microgauss, still incredibly weak by earthly standards, but over distances of millions of light years, they exert a powerful influence on nearly every physical process happening inside the cluster. How do such fields become so strong in a place that is, on average, far emptier than the space between stars? The answer lies in chaos. Clusters are not static structures. They grow by consuming smaller groups of galaxies, which crash into the main system at speeds of thousands of kilometers per second. These mergers generate enormous turbulence in the hot gas, stirring it into a frothing maelstrom. That turbulence stretches and amplifies any existing magnetic field, winding it up like a cosmic mixer until its energy reaches a balance with the turbulent motions of the gas. Computer simulations show that after a major merger, the field strength can increase by an order of magnitude or more, and the resulting structure becomes tangled and complex, a web within the web. This amplified magnetic field does not just sit passively. It actively shapes the behavior of the cluster gas in ways that astronomers are only beginning to fully appreciate. One of the most important effects is on heat conduction. In a cluster, the hot gas should, in theory, conduct heat very efficiently from the hot inner regions to the cooler outer edges. That process would smooth out temperature differences and eventually cause the gas to cool and collapse, feeding a steady stream of material toward the central galaxy. But observations show that the gas remains hot and stratified, with sharp temperature gradients that should not last. Magnetic fields are the reason. When the field lines are tangled on small scales, they dramatically reduce the ability of electrons to transport heat across the cluster. The electrons are forced to spiral along field lines, but the field lines themselves do not connect the hot and cool regions directly. The result is that heat conduction is suppressed by a factor of 100 or more, preserving the hot core and preventing runaway cooling that would otherwise drain the cluster of its gas. The same tangled magnetic fields also control the lives of cosmic rays within the cluster. Supernova, active black holes, and merger shocks all inject high-energy particles into the intracluster medium. Without magnetic fields, these cosmic rays would stream away freely, escaping the cluster in a relatively short time, but the fields trap them, forcing them to diffuse slowly through the gas. As they wander, they collide with ambient photons and produce gamma rays, and they also generate radio emission when they spiral along the field lines. This radio emission is what allows us to see the magnetic fields of clusters directly. Astronomers have discovered that many clusters glow with faint, diffuse radio emission that fills the entire cluster volume, not just the individual galaxies. These are called radio halos, and they typically cover millions of light years. The emission is smooth and unpolarized, and it requires both a population of relativistic electrons and a magnetic field of about a microgauss spread throughout the cluster. The electrons that power radio halos are thought to be accelerated by the same turbulence that amplifies the magnetic field, creating a self-sustaining cycle where the field and the particles reinforce each other. In addition to halos, some clusters also host radio relics. These are bright, elongated structures found at the periphery of clusters, often tracing the location of a merger shock wave. When a shock plows through the intracluster medium, it accelerates a fresh population of electrons to high energies, and those electrons light up as they spiral in the compressed magnetic field behind the shock. Relics are not diffuse like halos. They are narrow and polarized, revealing the ordered structure of the shock-compressed field. By studying relics, astronomers can map the location of merger shocks and measure the magnetic field strength at the cluster edge, which often reaches several microgauss. Together, halos and relics provide a dual window into the magnetic life of clusters, one showing the steady-state turbulent field, the other capturing the transient drama of cluster assembly. But radio halos and relics are not the only magnetic signatures. sensitive Faraday rotation measurements of background radio sources shining through clusters reveal detailed maps of the field structure. In the Perseus cluster, for example, rotation measure maps show a tangled field that is strongest near the central galaxy, where the supermassive black hole injects bubbles of magnetized plasma into the surrounding gas. Those bubbles rise buoyantly, stretching the field and creating cavities that are visible in X-ray images. The whole system is a dynamic interplay between magnetic fields, hot gas, and the black hole engine at the center. The presence of these strong magnetic fields in clusters raises a deeper question that reaches back to the earliest moments of the universe. Where did the original seed fields come from that mergers and turbulence later amplified to microgauss strength? The answer may lie in the very fabric of spacetime itself, in processes that occurred during the first fractions of a second after the Big Bang. Some of the most intriguing theories suggest that quantum fluctuations in the early universe could have generated magnetic fields so faint that they barely registered, yet they provided the initial spark that later cosmic events would amplify into the organized fields we see today. Those primordial fields would have been stretched and diluted by the expansion of the universe, but imprinted onto the first structures that formed, including the seeds of galaxy clusters. The transition from the turbulent fields of clusters to the ghostly primordial fields that predate them is a journey from the largest scales of the present universe to the smallest scales of the early cosmos. A journey that connects the magnetic webs of today to the quantum fluctuations of the beginning of time. That journey begins in the first trillionth of a second after the Big Bang, when the universe was a searing, expanding soup of energy and particles. In those earliest moments, the forces of nature were unified, and the universe was too hot for even the simplest atoms to exist. But as it cooled, it underwent a series of phase transitions, sudden shifts in the state of matter and energy, much like water freezing into ice. Each transition released immense energy and could have generated tiny magnetic fields from the chaotic quantum fluctuations that filled all of space. These are called primordial magnetic fields, and they represent the very first seeds of magnetism in the cosmos. One possible origin comes from the electroweak phase transition, which happened when the universe was about a trillionth of a second old. At that moment, the electromagnetic force and the weak nuclear force separated, and the process could have created magnetic fields through a mechanism called the Biermann battery or through the dynamics of bubble collisions. Another possibility involves inflation, the brief period of exponential expansion that stretched quantum ripples into cosmic scales. During inflation, quantum fluctuations in the electromagnetic field could have been amplified, leaving behind a faint but coherent magnetic field across the entire observable universe. The strength of these primordial fields would have been incredibly weak, perhaps only a billionth of a Gauss, far too faint to detect directly. But even such ghostly fields left their fingerprints on the cosmic microwave background, the ancient light that has traveled to us from when the universe was only 380,000 years old. As that light passed through the magnetized plasma of the early universe, its polarization was slightly rotated by the Faraday effect. By measuring that rotation pattern across the sky, scientists can set limits on how strong any primordial magnetic field could have been. The Planck satellite and other SIMBI experiments have placed tight constraints, showing that if a uniform field existed across the entire universe, it could be no stronger than a few billionths of a Gauss today. That may seem impossibly weak, but in the dense, hot early universe, even such faint seeds could have been amplified later by the turbulent collapse of gas into the first stars and galaxies. These observational limits are crucial because they narrow down which theoretical models are viable. For example, fields generated during inflation would leave a specific signature in the CMB, a slight increase in certain polarization patterns that has not been observed. That means inflation alone probably could not produce a field strong enough to seed the microgauss fields we see in galaxies and clusters today. More likely, a combination of processes worked together, with initial seeds from phase transitions or inflation later boosted by dynamo action in protogalaxies and by the mergers that built clusters. To test these ideas, researchers turned to magnetohydrodynamic simulations, or MHD simulations. These are computer models that treat the gas and magnetic fields as a single fluid, obeying the laws of electromagnetism and hydrodynamics. By plugging in different initial seed strengths and watching how they evolve under the pull of gravity and the push of supernova explosions, the simulations reveal which seeds survive and grow into the fields we observe. They show that if the initial field is too weak, it gets shredded by turbulence and never reaches the required strength. If it is too strong, it suppresses star formation and changes the galaxy structure. The sweet spot lies in a narrow range, exactly the kind of seeds that phase transitions and early dynamos could produce. These simulations also help explain why the cosmic web itself seems to be magnetized. As gas flowed into the filaments that connect galaxy clusters, it carried with it whatever magnetic seeds had been planted in the early universe. The turbulent motions within those filaments amplified the fields, creating the faint synchrotron glow that radio telescopes have barely begun to detect. So the imprint of primordial magnetism reaches all the way from the quantum foam of the Big Bang to the largest structures we see today, a continuous thread connecting the smallest scales of particle physics to the grandest scales of cosmology. And as our simulations grow more detailed and our telescopes more sensitive, that thread is slowly coming into focus, revealing how the invisible became the architect of the visible. Magnetohydrodynamic simulations turn the invisible into the visible. Inside a supercomputer, researchers feed in equations that govern the motion of gas, the pull of gravity, and the push of magnetic fields all at once. The computer then divides space into millions of tiny cells and calculates how each cell changes over time, step by step. This is how we watch a galaxy form on a screen, or a star ignite in a cloud, or a jet blast away from a black hole, all driven by the same magnetic forces that we have been tracing through the cosmos. These models are called MHD simulations, short for magnetohydrodynamics, and they have become one of the most essential tools in astrophysics. They allow scientists to test ideas that would be impossible to observe directly, like how a weak seed field from the early universe can grow into the ordered spirals we see in galaxies today. Two of the most widely used codes in this field are called Athena and Pluto. These names sound ancient, and they are, in a way, because they are built on decades of mathematical and computational research. Athena is designed to handle a wide range of problems, from the turbulent collapse of interstellar gas to the violent merger of galaxy clusters. It uses a technique called Gojunov's method, which tracks how shock waves and magnetic discontinuities move across the grid. Pluto, on the other hand, is optimized for studying relativistic plasmas, where particles move at speeds close to light, and it includes advanced modules for handling the extreme magnetic fields near neutron stars and black holes. Both codes have been used to simulate the evolution of cosmic magnetic fields from the earliest protogalaxies all the way to the massive clusters we observe today. In these simulations, you can watch as a tiny seed field, perhaps just a trillionth of a Gauss, gets stretched and twisted by the turbulent motions of collapsing gas. Over hundreds of millions of years, the field amplifies, reaching the microgauss strengths that radio telescopes detect. The simulations also reveal how the field organizes itself, forming coherent spiral patterns in the disks of galaxies and tangled webs in the hot gas of clusters. Without MHD simulations, we would only have snapshots and theories, isolated pieces of a puzzle. With them, we can see the entire story unfold from beginning to end, a digital journey through time that turns the universe's hidden magnetic skeleton into a moving, breathing picture. And as the simulations grow more detailed, they are beginning to answer one of the deepest questions left. How did the very first magnetic fields in the universe come into being? The very first magnetic seeds emerged from chaos itself. In the early universe, long before stars or galaxies existed, the cosmos was filled with a hot, uniform plasma of protons, electrons, and radiation. That plasma was nearly perfectly smooth, but not entirely. Tiny differences in pressure and temperature created slight flows of material, and where those flows met, the Zeeman battery kicked in. Named after the German physicist who first described it, this process works like a natural generator. When protons and electrons move together in a plasma, they tend to stay coupled because of their opposite charges. But if a pressure gradient pushes them unevenly, the heavier protons lag behind while the lighter electrons surge ahead. That separation creates an electric current, and a current always generates a magnetic field. The fields produced by the Zeeman battery are incredibly weak, far weaker than even a microgauss, but they are the first sparks of cosmic magnetism. Another seed mechanism, the Weibull instability, operates in a different way. When streams of charged particles flow past each other at high speeds, tiny fluctuations in their positions can grow explosively. The streams twist and tangle, generating magnetic fields out of pure kinetic energy. This instability is especially important around shocks, like those from the first supernova or the collisions that formed the first galaxies. The fields it produces are also faint, but they can appear rapidly and in many places at once. Once these seeds exist, they need to grow. That growth comes from dynamo amplification, a process that has appeared many times in this story. In a turbulent, rotating medium, like the early gas that would become a galaxy, magnetic field lines get stretched, twisted, and folded. Each twist amplifies the field slightly, and over hundreds of millions of years, a seed field that was 1/1,000,000th of a Gauss can become 1 microgauss, strong enough to shape galactic structure. Observations put tight constraints on this process. If the seeds were too weak, they would never reach the observed strengths within the age of the universe. If they were too strong, they would suppress star formation and alter the cosmic web in ways we do not see. The narrow range that works points to a delicate balance, one that the early universe apparently achieved. And those same amplified fields do not stop at the galactic scale. They are carried into the hearts of collapsing clouds where they wrap around newborn stars. The star itself inherits that magnetic field, compressing and strengthening it as it condenses. That inheritance marks the beginning of stellar magnetic fields, the very fields that drive flares, wind, and activity on the Sun and every other star. So the thread runs from the first quantum fluctuations to the surface of a star, a continuous chain of magnetic birth and growth that connects the smallest scales to the largest. And when we look at a star like our Sun, we are seeing the endpoint of a process that began in the first seconds of the universe. A star's magnetic field does not stay frozen in time. It evolves alongside the star itself, sculpting its rotation, draining its mass, and ultimately steering its fate. On the surface, this magnetic activity reveals itself through dark star spots, like the spots on our Sun, but often far larger and more numerous, and through brilliant flares that erupt when magnetic field lines snap and reconnect. For low-mass stars, those cooler, dimmer cousins of the Sun that make up the vast majority of stars in the galaxy, this magnetic activity is especially powerful and persistent. It acts as a cosmic brake. As a star spins, its magnetic field interacts with the surrounding plasma, launching a steady wind of charged particles that carries away angular momentum. Over billions of years, this magnetic braking slows the star's rotation, from a fast spin in its youth to a slow, steady crawl in old age. The slower a star spins, the weaker its magnetic dynamo becomes, creating a feedback loop that gradually quiets the star. This process has profound consequences. A star that loses its spin too quickly may never generate the intense flaring that can strip away a nearby planet's atmosphere. But a star that remains magnetically active for too long can bombard its planets with harsh radiation and energetic particles, making life difficult to sustain. To understand this dance, astronomers use a powerful technique called Zeeman Doppler imaging. By observing spectral lines that split in a magnetic field and mapping how those shifts vary as the star rotates, they reconstruct the star's surface magnetic field in exquisite detail. The results reveal complex patterns, not simple dipoles like Earth's, but tangled networks of active regions, often concentrated at the poles or in bands, changing over cycles just like the Sun's 11-year rhythm. This solar-stellar connection is the foundation of our understanding. By studying the Sun up close, we can model how other stars behave, and by observing those stars, we see how different masses and ages alter the magnetic story. The same magnetic field that drives sunspots and solar flares also shapes the environment around any exoplanet that orbits that star. When a planet passes through a star's magnetic field, it can induce currents in the planet's own atmosphere or interior, producing detectable radio emission or even shaping the planet's own magnetic shield. The star's magnetic activity does not just affect its own evolution, it writes the conditions for any world that calls it home. And as we turn to those distant worlds, we find the magnetic thread continues, linking the life of a star to the potential for life on its planets. A planet's magnetic field determines whether it keeps its atmosphere or loses it to the star. When a world orbits close to its sun, the star's relentless wind and radiation can strip away lighter gases over time. But if that planet possesses a strong enough magnetic shield, it deflects the charged particles, preserving the delicate envelope of air that might one day support life. This is why astronomers are so eager to measure the magnetic fields of exoplanets, to understand which worlds can hold onto their atmospheres and which are doomed to become barren rocks. Detecting these invisible fields from across light years is a formidable challenge, but nature offers a clever signal. When a planet moves through the magnetized plasma of its star's wind, it generates a faint but distinct radio emission, much like the auroral radio bursts from Jupiter and Saturn. This emission, typically at frequencies of tens of megahertz, is produced by electrons spiraling along the planet's magnetic field lines, a process called the electron-cyclotron maser instability. Radio telescopes on Earth, like the Low-Frequency Array or LOFAR, are now sensitive enough to pick up these whispers from distant worlds. In 2020, LOFAR detected what appeared to be radio emission from the star system Tau Boötes, likely coming from a hot Jupiter orbiting close to its star. The signal matched predictions for a planetary magnetic field several dozen times stronger than Jupiter's own, a field robust enough to shield a close-in world from the harshest stellar assaults. But radio detections are rare and difficult to confirm, so astronomers are turning to other methods. The James Webb Space Telescope, with its powerful infrared eyes, offers a new window. When an exoplanet passes in front of its star, some of the starlight filters through the planet's upper atmosphere. By analyzing the spectrum of that filtered light, JWST can detect the presence of molecules like water, methane, and carbon dioxide. But crucially, the shape of these spectral features can also reveal the presence of a magnetic field. A strong field would heat the upper atmosphere and alter the distribution of particles, leaving a subtle imprint on the transmission spectrum. Future JWST observations of promising targets, like the TRAPPIST-1 planets or the temperate world LHS 1140b, will search for these magnetic fingerprints. Knowing a planet's magnetic field strength is not just a curiosity. It tells us how long that planet can hold onto its water, how it interacts with its star's wind, and whether it might generate its own protective aurorae. Some worlds might even have magnetospheres that connect directly to their star's magnetic field, creating a vast circuit of current that can transfer energy and matter back and forth. This star-planet magnetic coupling can drive flares on the star and heat the planet's upper atmosphere, affecting its long-term evolution. As we uncover these invisible connections, we realize that exoplanets are not isolated spheres. They are embedded in a magnetic ecosystem that links them to their star and to the larger galactic environment. And the principles that govern these interactions, magnetic reconnection, induction, and dynamo action, are the same ones that drive the most violent events in the universe, from stellar flares to the jets of black holes. The same snap of field lines that lights up an aurora on a distant world can also trigger a flare on its star, and that flare can in turn reshape the planet's magnetic shield. The cosmos, it seems, is held together by a web of invisible threads, and every new exoplanet detection adds another strand to that web, another place where the magnetism that has shaped the universe from its first moments continues its silent, ceaseless work. Magnetic reconnection is the universe's most efficient energy release mechanism, and it operates in environments that span the full range of cosmic violence. On the surface of a star like our Sun, reconnection between tangled field lines triggers solar flares, sudden explosions that can outshine the entire star for minutes. But the same process scales up dramatically. In the magnetospheres of neutron stars, the fields are so intense that reconnection can unleash gamma-ray bursts, some of the brightest events in the sky. For magnetars, the most magnetic objects known, a single reconnection event can crack the star's crust and release more energy in a fraction of a second than the Sun will produce in 100,000 years. In every case, the basic mechanism is the same. Magnetic field lines break and reconnect into a simpler configuration, converting stored magnetic energy into heat, particle acceleration, and radiation. The speed and efficiency of this conversion depend on the plasma conditions. In the hot, nearly collisionless plasmas found in stellar coronae and magnetospheres, the standard models of reconnection fail to predict the rapid rates we observe. That is where kinetic simulations come in. These computer models treat particles individually, tracking how electrons and ions interact with the electric and magnetic fields at the reconnection site. By simulating millions of particles over a small region, researchers can see the microscopic instabilities that allow reconnection to proceed so quickly, such as the formation of thin current sheets and the generation of intense electric fields that accelerate particles to near light speeds. These simulations are computationally expensive, often requiring weeks on the world's largest supercomputers, but they are essential for understanding how reconnection powers everything from the aurorae on Earth to the most distant gamma-ray bursts. As computing power grows and algorithms improve, these models will become more realistic, incorporating the complex magnetic geometries of real astrophysical objects. The next generation of observatories will put these simulations to the test. The upcoming Solar Orbiter and the future European Solar Telescope will watch reconnection happen on the Sun with unprecedented resolution, capturing the very moment field lines snap. Telescopes like the Square Kilometre Array will map the radio glow from reconnection in distant galaxies and cluster halos, and X-ray observatories such as the Athena mission will peer into the hottest regions around neutron stars where reconnection drives the most violent flares. Together, these tools will bridge the gap between the microscopic dance of electrons and the colossal outbursts that reshape galaxies. The thread of reconnection runs through the entire cosmos, from the smallest spark on a star to the most powerful explosions we have ever detected, and soon we will be able to follow it with a clarity that once seemed impossible. The telescopes that will map these invisible fields are already being built, and they promise to reveal a universe far more magnetically rich than we ever imagined. The Square Kilometre Array, or SCAR, will be the most powerful radio observatory ever constructed, with dishes spread across South Africa and Australia. When it comes online in the late 2020s, it will survey the entire southern sky with a sensitivity hundreds of times greater than any existing instrument. For magnetic fields, that means it will detect the faintest synchrotron glow from the cosmic web, the diffuse radio emission that we have only glimpsed from a handful of clusters. The SKA will map the Faraday rotation of millions of distant galaxies, building a three-dimensional picture of the magnetic field across the entire observable universe. It will see how those fields change with cosmic time, how they evolved from the first seeds in the early universe to the ordered structures we see around us today. Meanwhile, the low-frequency array, or LOFAR, is already operating, but its full potential is just beginning to be realized. LOFAR observes at the lowest radio frequencies that reach Earth, frequencies that are especially sensitive to the faintest, most extended magnetic structures in clusters and filaments. Early LOFAR observations have already detected the first diffuse radio emission from the space between galaxy clusters, opening a new window onto the intergalactic magnetic field. A planned expansion called LOFAR 2.0 will increase its sensitivity and resolution, allowing it to detect the magnetic fields that thread the largest voids in the cosmos. Another major facility on the horizon is the next-generation Very Large Array, or NGVLA. This will be a network of over 200 radio dishes spread across North America, operating at higher frequencies than LOFAR and the SKA. The NGVLA will zoom in on the magnetic environments around black holes, resolving the structure of accretion disks and jets with unprecedented clarity. It will also detect the polarized emission from the interstellar medium of nearby galaxies, tracing how magnetic fields shape star formation on the scale of individual clouds. Together, these three observatories will cover the entire radio spectrum from the lowest frequencies to the highest, providing a complete picture of cosmic magnetism. They will allow us to answer questions that have lingered for decades. How strong are the magnetic fields that fill the cosmic web? Do they vary from one filament to another? What role do they play in channeling gas into galaxies? And perhaps most profoundly, can we detect the weak, tangled fields that may have been left behind by the very first stars and black holes, a fossil magnetism from the dawn of cosmic structure? Each new detection will refine our models, and each new map will reveal another layer of the invisible skeleton that binds the universe together. The thread that began as quantum fluctuations in the first moments of time will be traced to the largest scales we can observe, and we will finally see the full picture of how magnetic fields have shaped the cosmos from its birth to the present day. Now we have traced that skeleton from beginning to end, from the first quantum whispers of the Big Bang to the vast magnetic webs that bind clusters of galaxies together. In 30 distinct yet interconnected ways, magnetic fields have shaped every layer of the cosmos. They slowed the collapse of gas clouds to birth gentle stars, stirred the disks that grew planets, and shielded those worlds from stellar winds. They twisted into spirals that guide entire galaxies, powered jets that blast away from black holes, and left their fingerprints on the oldest light in the universe. They have been the quiet architects of star formation, the engines of the most violent explosions, the guardians of atmospheres, and the invisible threads that lace together the largest structures we know. Without them, the universe would be a far simpler and far emptier place, a cold, featureless expanse where gas collapsed too quickly, planets lost their air, and galaxies never learned to spin. But because magnetic fields are everywhere, the cosmos is rich with complexity, beauty, and life. They are not a side note in the story of cosmic evolution. They are a central character, one whose influence we are only beginning to fully appreciate. So the next time you look up at a starry sky or marvel at an image of a distant galaxy, remember that what you see is shaped by forces you cannot see, forces that have been at work since the very first moments of time. And if you want to keep exploring these invisible wonders with us, hit that like button, subscribe to the channel, and drop a comment telling us which magnetic field phenomenon you find most fascinating: the gentle dynamo of a planet, the furious snap of a magnetar flare, or the silent grip of a galactic field. The universe is magnetic, and its story is still unfolding.